This presentation is not in line with the mainstream of the Amaden project. My name is Zlatan Šoškić. I am a participant in the Amaden project, and my part of work was calculation of production costs of additive manufacturing, which is still relevant for any additive manufacturing project, simply because additive manufacturing costs. In this presentation, we will first look into the structure of the additive manufacturing production costs in general, and then we will describe in more details the powder bed fusion technology production costs with the particular insights into the calculation of production costs of a batch of products with these technologies and an estimation of production costs of an individual product using powder bed fusion production technologies. Let me start first with a small notice about the ways we cannot use to calculate additive manufacturing production costs, because in general we cannot calculate additive manufacturing production costs using the volume of product and unit volume of product costs. Also, we cannot express the cost of additive manufacturing using unit mass of product. And finally, the complexity of the product shade does not influence additive manufacturing production costs, unlike the costs of other technologies. We are stressing this because a lot of customers are really requesting to give some estimation of prices of a unit volume of a product or unit mass of a product, and then they expect that simple products with simple shapes will have smaller prices than the products of complex geometry. Because all of this is not true, we have to start with stressing what is not the way to calculate additive manufacturing production costs. Then, how can we really calculate additive manufacturing production costs? Depends on the additive manufacturing technology that is used. Because one approach we are using when we are calculating the cost of the technologies based on melted wire, then on the technologies based on solidification of liquids, and the third approach we use for the powder bed fusion technologies. The powder bed fusion technologies are the topic of discussion of this presentation, and I'll comprise with powder bed fusion technologies selective laser sintering, direct laser metal sintering, and multi-jet fusion. Selective laser sintering is providing us with the possibility to produce plastic products. Direct laser metal sintering is providing us with the possibility to produce metal products, and multi-jet fusion technology is a rather new technology for production of plastic products. Besides these technologies, there are other powder bed fusion technologies like electron beam melting, and the principles of cost calculations are the same. No matter which powder bed fusion technology we use, the principle is the same, and it is presented here in this picture. On the top left picture, we see a production chamber, which consists of a product bin and powder container. Powder container contains the powder which is aimed for production. So this is a mixture, we will discuss it later. And the product bin is a space where the products are placed during the production, and they are supported by the surrounding powder that is unused. So practically in the product bin we have powder that is fused into products, and the powder which is not fused, which is not used, it is heated, its properties are changed, but it is still not used and may be reused under the conditions that we will discuss a bit later. During the production process, recoater is moving one layer of the powder from powder container and deposits it over the top of product bin. As we see here, the recoater is moving on the right, and it leaves a thin layer at the top of product bin. After the removal of the recoater, starts selective action by laser or by other agents. It could be also infrared light, or it could be with the electron beam melting. It can be done with electron beam. But anyway, only a part of the top layer is melted, and a new layer of products is formed on the top. The product bin is then lowered, and the space is left for a new layer to be put, and the process is continuing until it is completed and all the products are manufactured. So after that, the product bin is removed, the products are being taken from the product bin after cooling, and then they pass to further phases of processing. The previous slide is showing us some very important features of powder-bed fusion technologies. The first is that it represents really a simultaneous manufacturing of a set of products called batch during a single production process using a single production chamber. So all the products are produced together, and the powder-bed fusion technologies as additive manufacturing technologies in principle represent thus collective production, or kind of collective production. So there are no real production costs of an individual product, and there are only production costs of a batch. So actually, whenever you want to calculate the production costs, they really can be only production costs of a batch and not of an individual product. In order to calculate the costs of production of a batch, it is useful to consider the complete production process chain, because the costs are arising even before the building process, before the manufacturing process starts, and to assess the costs of powder-bed fusion technologies, one may very well start from the analysis of the activity chain model, which is presented in the following figure. That figure is showing the process of powder-bed fusion, which starts really from developing of the models of products which are going to be produced. So the customer is providing to the manufacturer raw models, but these models have to be sometimes checked, sometimes corrected to be able to be manufactured in the optimal way using the additive manufacturing technologies. So in order to develop these fixed models, one needs to have obviously computer and modeling software, and has to have skilled designer, which is usually a mechanical engineer who understands very well the models and the possibilities of additive manufacturing technologies. These fixed models of all the products which are going to be produced in a single batch are assembled in a batch by another expert, the assembly designer, who is making a spatial distribution of the products, preparing them to be produced in an optimal way with the best possible accuracy, and using the space of a production bin in an optimal manner. For these purposes, besides his skills, he needs a special software for assembly and obviously a computer. The result of his work is the model of a batch, and this model is loaded into machine, and then the process is preparing for production by heating of the machine and everything else that is being achieved by also a specially trained operator. Once the job is ready, building, which is described at the figure that we discussed previously, starts, and using the powder, the machine, and the energy, product bin is being filled with products, and after the completion of the job, starts the phase of removal. So the products are removed from the product bin, and we need, for this purpose, operator who is using the machine and energy, taking out the products which have some powder still attached to them. So the products have to be put into the blasting cabinet and blasted in order to remove that excess powder which is connected to their surface. So we need abrasive, we need a trained operator, we need cabinet, and we need energy. And after the process of blasting, we are really having raw products that may be subjected to post-processing, but it is being done by other technologies and does not really belong to the production, to the activity chain model of powder bed fusion technology. Now, using the activity cost model presented at the previous slide, we may calculate the production cost, and the calculation starts really with the separation of the production costs into the direct production costs and indirect production costs, as it is the case with other production technologies. So we may write the cost of a batch as a sum of its direct and indirect costs. Direct costs represent the cost that can be attributed to a specific batch, so the production of a specific batch. And they are expressed as the sum of direct costs of all activities that are being performed during the production of the batch. So they can be expressed as a sum of the direct costs of the modeling, assembly, setup, building, removal, and blast activities. For each of these activities, the direct cost may be expressed as a sum of labor costs, material costs, and energy costs. And therefore, each of these elements of the direct cost can be expressed like this, with the sum of three elements. The labor costs of each of the activities can be separated into the designer costs and operator costs. Designer costs are the cost of the work of engineers, which are typically higher than the cost of the work of operators, and they are arising in the phases of modeling and assembly. The designer labor costs can be expressed as the production of the hourly rate paid to designers and the time for the specific operation and activity, which may be modeling or assembly. Operator costs arise in the phases of preparation, removal, and blasting, and can be expressed in a similar way, just using the time unit costs of the labor of operators. Material costs arise in the phases of building and blasting. The material costs of building comprise powder costs and the cost of fusion agent and detailing agent, which is typical for multi-jet fusion technology. The blasting material costs comprise really abrasive that is used during the blasting. The most important thing that should be stressed when one discusses material cost of building is that the material which is used in the powder bed fusion technologies is really a mixture of powders. So from one side, we are using already used powder, which is really reused from the previous production processes. It is still usable, but its properties are a bit changed. So it has to be mixed with fresh, non-used powder with a certain amount, which we call refreshment rate, R. And the refreshment rate depends on material that is used. Sometimes it is like 50%, sometimes goes to 75%, but certainly one part of the powder is already used and it does not really represent the cost. So once we use some material in a process, only a part of it is fresh powder, only a part of it represents really a cost for us, because we always have high amounts of the already used powder to mix, and its cost is really not relevant for us anymore. The material costs in the building process consists of two parts. The first is a part of fixed consumption, and the second part is a variable consumption. Fixed consumption represents a layer of powder that is used as a support to the remaining of the batch. That layer is, depending on technology, of various thickness, but it varies between, let's say, a couple of millimeters to a couple of centimeters. And that thickness of that layer and the amount of consumption doesn't depend on the contents of a batch. On the other hand, the variable consumption is the part of consumption that depends on the number of products, that depends on the volume of products, and it's really expressed through the height of the batch. So having in mind what we previously said, we can calculate the costs of building powder by multiplying the unit cost of the powder, the mass of the powder, with the used mass of powder. And it is only a percent of the complete mass of powder, which is really a product of the density of the powder and the total volume of powder, which consists of two parts, so the fixed volume and the variable volume, which is proportional to the height of the production batch. So we see here that the critical role in the material costs, which are quite high in powder bed technologies, plays the height of a batch. And the height of the batch depends on the spatial distribution of the products in a batch. So it depends really on the assembly designer skills. So assembly designer is the one who is really determining the height, but he also has to follow some limitations, some rules about the distances between parts. He has also to keep in mind the anisotropy of accuracy of production process, which has higher deformations in a horizontal plane than in the vertical direction. Also, the number of products in a batch is important, obviously, for the height of a batch, and the requested production time, because in order to reduce the time of production, then we have to reduce the height of a batch, no matter that it may cause some inaccuracy of geometry of produced parts. It is very important to understand here the role of the height and the importance of orientation of a part during the production process to the production costs. So let us assume that we need to produce only one product and that it has very different dimensions. So if we produce it in this horizontal orientation, the total height of production batch will be very small, let's say a couple of centimeters. But in the case that we insist very much on the accuracy of dimensions, then we may produce it in the vertical orientation. And then you may see that the height of the production batch is like 4 times higher, and the consumption of the new powder consumption and the variable material costs will be like 4 times higher than in the first case. So it is not only what we are producing, but the orientation is very important, and it affects a lot the production costs. Another aspect, due to the dependence of the height on the number of products, is that the costs of individual product may vary a lot. Let us see here as an example production of a small ball. So really one sphere which is produced within production volume, and let us assume that the cost of the material with this height is like 15 euros. So for production of this part we have to spend 15 euros for material costs. So if we produce 5 instead of 1 part, then we may reduce the cost to 3 euros per part. And it is for production of 5 parts. But if we produce the 6th part, then the total cost of the batch will grow to 30 euros. And since we produce 6 parts, then we will have the cost of 5 euros per part. So in this assembly, the cost of production of 6 parts per part is higher than production of 5 parts, and it is not that it is a small increase. Now, if we produce 10, the price is also going down to 3 euros per part, but you see that we achieve very small material costs, even with 5 spheres, and the increase of the parts then to 6 and to 10 didn't contribute to reduction of the material costs per part. Finally, in the category of direct production costs, we need to discuss also the energy costs that arise in the phases of preparation, building, and blasting. Preparation costs are practically always the same, because the operations that need to be done are always almost the same. So they are really fixed energy costs, and they may be calculated by multiplying the unit costs of energy with the time for preparation and the power of the machine during the preparation phase. The building costs, on the other hand, building energy costs, depend on duration of the process, which in turn depends on the height of a batch and also on a spatial distribution of the products in a batch. Because if all the space is filled, then the production is going to last longer than if there is a lot of empty spaces between the products. So the building costs, building energy costs, may be calculated on a very similar principle using the duration of the building and the power of the machine in the building phase. Finally, the blasting costs can be separated into the blasting cabinet consumption cost, which is calculating using the same principle, so the time of blasting and the power of blasting cabinet, and the air compressor consumption, because the cabinet uses also the air compressor in its work, but it does not use the whole capacity of the air compressor, and the calculated cost of the air compressor during blasting should be multiplied by the ratio of the air consumption of the cabinet divided by the air capacity of the compressor. Thus, we come to indirect production costs, and the indirect production costs can be separated into the equipment costs, overhead costs, and other indirect costs. It should be noted that the indirect production costs are exceptionally high for all additive manufacturing technologies, and thus they are very important to be calculated as well. The equipment costs can be divided into the machine costs, software costs, and consumables costs. The usual way to express the equipment cost is to calculate their time unit costs, because then later the total costs of equipment are calculated by multiplying the unit cost, time unit cost, with the duration of certain operations. The time unit costs of equipment can be separated into machine time unit costs, software time unit costs, and consumables time unit costs. Machine time unit costs comprise purchase and depreciation costs for the machine, but also very high maintenance costs. And the machine time unit costs can be calculated for each of the machines by dividing the purchase and depreciation costs with the estimated number of hours during 1 year. So the whole duration should be multiplied by utilization rate of the machine. And then we obtain thus the number of working hours per year. The total cost is then consists of the purchase cost divided by the number of years for depreciation and the annual maintenance costs that have to be performed each year. A similar approach may be used also to calculate the software time unit cost with one difference, that the software is usually bought for a certain number of licenses, and then we need to calculate the purchase costs and annual reactivation costs divided by this number of licenses. So this is the formula, which looks quite similar to the formula used for calculation of machine time unit costs, but the difference is that now we are dividing also the cost with the number of software licenses that are bought simultaneously. Speaking about consumables time unit costs, we usually have just estimation of annual consumption, and then we calculate the time unit cost by dividing the product of number of packages that are used per year of a certain consumable with the unit price of a package of consumables, and then we divide this with the number of working hours, because the consumables are also proportional to the building time by the time of use of a machine. Speaking about indirect production costs, we come to the final two categories. First, the overheads, so the costs that exist even without production. These are the cost of management and administration, then the cost of renting or purchase of rooms, and finally the cost of heating, water, electricity, and all other costs. And they are quite complex to calculate, and the usual methodology is to estimate the overheads as a part of the cost, which is proportional to the sum of direct costs, energy costs, and other indirect costs. These other indirect costs are connected to the production process, and they do not represent directly the production. So these are, for example, costs for material handling and disposal, or the transport costs and other costs, and they can be estimated using some previous experiences on the base of the consumption of the other indirect costs in a certain period, depending on obviously the number of production hours, and they are being proportional to the building time, because they are still connected to the production. In this way, we described the calculation of all the categories of the costs that are entering into the calculation of product cost of production of a certain batch. But if we want to think about the cost of individual product, it is quite complex in this case, because we notice that the common costs are independent of production volume. So they are not reduced with the number of products. So the division of this cost is not having any sense. The number of products, on the other hand, is relevant for the product cost, but the influence of the number of products, as you noted on some examples, is not straightforward. The batch volume and the height are really the factors that are most connected to the production cost of a batch. But if we want to develop a methodology for rough estimation, we need to make some assumptions. And one way to do it is to notice that modeling and overhead costs increase with number of types of products and not the number of products. So if you have to produce 100 of identical products, then you really need just to fix one model. And also the overhead costs are not changed. And if you have to produce 100 different models, then you have to make 100 models. And the overhead costs are also increased because you had to handle all these costs with your customers. On the other hand, assembly, preparation, removal, and other indirect costs increase with number of products, no matter if they are of the same type or different type, because you need to take out and put in any of the products during the production process. You have to handle each individual product. Then the building costs increase with volume of products. The increase in the cost is not simple, but anyway, you can conclude that if you have higher volume, you will have higher building costs. The blasting costs, on the other side, increase with the surface of products, because it is the complexity of product that influences also the time of blasting. And now we define some assumptions on the dependence of the costs on the number of products and types, and we may devise a formula. So let us assume that we have T product types in a batch, and with NK we will denote the number of products of the type K. So K can be 1, 2 until T. If the total volume of all products of type K is Vk, and with Sk we denote total surface of products of type K, then we can calculate the ratio, the contribution of the products of type K to the total number of products, and also the contribution of the volume of products of type K in the total volume of products, and also the ratio, which is contribution of the surface of products of type K in total surface in one batch. And then we may derive a formula like this, which is showing you how we may calculate, or at least estimate product cost of an individual product of type K by dividing the number of these products with the cost which is attributed to the products of type K. So modeling costs and overhead costs are divided by the number of types, and the other costs are scaled in a proportional way, with being proportional to the number of products, or to the volume of products, or to the surface of the products of certain type. One thing you may notice is that all the formulas used in the previous slides are quite long, and the production cost calculation is quite a complex process, and it includes a large number of parameters which are describing the costs of different categories that we noticed. So, for example, for selective laser sintering technology, we need 66 parameters to describe the production cost using the methodology that we described. And for multi-jet fusion technology, these are 76 parameters. when speaking about the direct metal laser sintering technology, the things are even much more complex, because we also have to include the cost of the supports which are used during the production to prevent some unwanted effects in production process. Then we need also to include the inert gas consumption, because this process is always made in an inert gas atmosphere. And in total, model for calculation of DMLS costs has up to 130 parameters. So we may conclude that it is quite a complex task, and it is really not possible to make simple estimations on the cost of production using just the shape of a product or its surface volume or any other simple property. So this was really an introduction to the calculation of production cost of additive manufacturing technologies. And if you have some questions, you may address Amada website, and I will be more than happy to discuss it with you or try to help you.